Okay, to finish section 12.5, triple integrals, we had finished this example in the previous video, the one of two videos. This is the second of two videos. I wanted to point out one more error that happened in this. There's nothing wrong with the overall answer and the technique we used, but note that at the beginning, this integral had a limit of integration along the y-axis with a negative root 9 minus x squared. In the previous video and notes, that was a 0 here. It just switched. That was just a typo, essentially. Of course, we could blame it on the fact that my heart was set on integrating in terms of polar coordinates instead of that, so I was jumping to those zeros too soon. Of course, we didn't integrate with respect to y and x. We switched to polar coordinates, so that mistake really didn't matter so long as we got the region D correct in polar coordinates, which we did, and that's fine. I just wanted to point that out in case any viewer or student wondered what happened here. That was just a typo. Okay, so we have two more examples to consider, and the first of which is probably one of the hardest types of problems in this section. And really what it's pointing out to us is the difficulty of setting up one of these integrals. Now they ask us in this example to express the iterated integral, this is the iterated integral that we're given, as a triple integral, and then as an iterated integral in a different order, integrating with respect to x, then y, then z. Okay, what we're given is one that's integrated with respect to z, then y, then x. We want to switch that to x, then y, then z. So it's not as simple as it might have been for rectangular regions. Okay, we saw that in 12.3 double integrals, that we had to be careful how we rewrote things. We usually had to invert a function to change our limits of integration. So it's not so straightforward as saying, okay, we just need to switch x and z's limits of integration here and we'll be all done. Realize if you did that, for the first objection to doing so, if we did that, this integral, these limits would be our final limits of integration. We would end up with a function of y being the result of our integral, which would be essentially meaningless in our situation. We should come out to a numerical integral for all of these. So that's one objection to it. The second we'll see below as we start to look at what this region E that's being described here looks like. So to express the iterated integral as just a triple integral, a general triple integral, we write it like this. Our differentials collapse to dv. We're integrating a rectangular region E in R3. With respect to volume there. So that's our triple integral, using Fubini's theorem to rewrite our iterated integral as that. And we want to pop out of this triple integral back into an iterated integral in the orders dx, dy, dz. So we need to identify what E is. And that's going to be described to us by these limits of integration. So remember that this one describes, it's a surface bound for our solid along the z-axis. This is a curve bound for our solid along the y-axis, and then x is limited to between 0 and y. So write all of this down essentially. Z is between 0 and 1 minus y. These are all coming directly from the limits of integration. This is an easier part of this. Root x to 1 is y's values, and 0 to 1 is x values. Okay, so these are the points x, y, z, which satisfy all three of those limits of integration, or the bounds determined by the limits of integration. Now let's have a look at the projections of each of these. The easiest one to come up with is this one. Y is between square root of x and positive 1. So that's this region right here. Y equals root x. It's everything underneath that curve. We stop it at x equals 1 because, well, that's x is equal to 1 is our largest value of x, and it goes from 0 to 1. Now, this tells us that z is between 0 and 1 minus y. So in other words, z is within this little region right here from z equals 0 up to 1 minus y. We note that this is a surface bound, right? So this is, but the function z is bounded by does not involve x. Neither one of them involve x, which means that this 1 minus y, z equals 1 minus y, is not just a line with respect to our solid, it's a plane, because x is allowed to vary wherever it might like. So what we have, when we look at the picture below, we'll get to what the details of it are, we realize right away that we've got a plane z equals 1 minus y that extends in all directions along the x-axis. So what might be better seen is maybe not necessarily in the drawing, but we do kind of see that planar region that's being pointed at by z equals 1 minus y. We might think of this as this line extends into and out of the page along the x-axis. And that's what forms that plane or that surface boundary of this region. The other surface boundary will be below, or could potentially be below. That's how it was given to us. That's the z equals 0, or the xy surface boundary. So that's what we were given to begin with. So that was our surface, the xy plane. This is our surface plane, z equals 1 minus y. Now our last projection is one of the harder ones to see. And what we get is on the zx plane, or the xz plane, z is actually in this region. And you can visually see this if you do a decent job of graphing the region. That's not probably the best way to go. What's probably easier to do is to involve both of these inequalities to see how z and x might relate to each other. So we'll start with the second inequality, that root x is less than y is less than or equal to 1. And I'll make it negative. Negative 1 is less than or equal to negative y less than or equal to negative root x. Why would I do that? Because z and y relate to each other through a negative y here. So carrying this out, I'll add 1 to all sides. So I'll have 0 is less than or equal to 1 minus y, which is less than or equal to 1 minus root x. Now I know when I see z is less than or equal to 1 minus y that I can relate z and x to z is less than or equal to 1 minus root x. So z is between 0 and 1 minus root x. This comes from this. Okay, so now I've shifted it to, this would be its own plane in its own right, its own cylinder in its own right as 1 minus root x. Okay, we'll see that a little bit later when we get into the details of this solid itself. But z equals 1 minus x is graphed here, and that's why z is within this region here. So we have an idea of what each of these projections looks like, and maybe we need to do the algebra that we've done here. Maybe we can see it in the graph. I recommend a combination of both in pretty much every example to be sure about what you're actually dealing with. But now it's time to have a look at this graph then. Okay, so this is our plane, z equals 1 minus y. So we've got that planar portion of the solid. We know that in xy, we have y equals the square root of x. So this curve here is y equals the square root of x. And extended into a cylinder, we see it traveling upward along the z-axis. It doesn't involve z, so it just stands straight up. So it's this, it could also be considered its own surface, right? In fact, if we're going to integrate first with respect to x, we need to get bounds on x. It looks like x is bounded by the xy plane in the background of this cylinder back here, right? And it's bounded in the front by the lines we've been pointing out by this cylinder here. And it's fully bounded by that because that comes to a point up front here, and these are all of our x bounds, xy parallel to the zy, or x parallel to the yz plane. So now we have some idea of what our surface bounds for x are, and if we're going to integrate with respect to x first, that's exactly what we need to know. We need to know what its surface bounds are, and that's 0 to square root of x. I'm sorry, 0 to, we need to express that in terms of y, so what we do is we take this equation and we re-express that as y squared equals x. So we know that x will range from 0 to y squared, to get that correct. So that's the first thing we're able to put down in our set describing E. So a goal of this, or a good idea, is to take our original description of E and rewrite it first so that we are bounding things in the ways that we'll need to for the integral. If we're going to integrate with respect to x first, then we need to bound x by surfaces. And these are the two surfaces. X equals 0 is the yz plane, and x equals y squared is the the parabolic cylinder, x equals y squared. Okay, so now we've got our surface bounds for x. Next, we're going to integrate with respect to y is what we're asked to have next in this integral. I'm not addressing the integral itself yet. I'm just using that as the orders that they're asking for. And now we're going to bound y, and we need to bound y along z, right? We need to bound y in the yz plane because we're bounding x by things parallel to the xz plane itself, and that parabolic cylinder we looked at previously, x equals y squared. So now we need to figure out the region in the yz plane. That one's quite a bit more straightforward. We know that y ranges from, and we could choose, since y has to be next, we need to find bounds for y. Well, y travels between 0 and 1 minus z. Right, those are all our values that y ranges along between 0 and 1 minus z. Now that being the case, we write it in. It's nice and straightforward. That's the projection. Also, that's our d, the projection of the solid E onto the YZ plane. So we've met that challenge. That's usually one of the hardest, is to get that second one right. In this case, this one wasn't very straightforward either, but we were able to do so. And then lastly, Z ranges from 0 to 1. That can be seen along this axis right here, along these points of intersection. So once we put them all together, our triple integral, written as an iterated integral with respect to x, then y, then z in these integrations, is literally just these limits, or these intervals, put in as our limits of integration, and we've got the desired answer. We could do that for dx, dz, dy. That's a pretty easy change. What would happen there is we'd have 1 minus y there, and y would go from 0 to 1. It's kind of a little bit of a cheat, but it's an easy one to do. dx, dz, dy would be that. There are some problems which will have you do this for all 6 different ways that we could express the iterated integral, which means you might be coming back to this drawing a few times and reconfiguring the way that you express your set E. Now, how did we get this drawing? That's one thing that I kind of quickly moved through. That was from really above and a little bit of help from the projections. Okay, it's clear that our projection here tells us that this is some plane, as I pointed out before, extending in and out of the page along the x-axis. Okay, now next, our projection on the xy plane was down here, y equals square root of x. We mentioned that as well. So where this curve intersects this plane is this curve right here. The work we did to find what that was massaging this equation so that we can relate x to z through this inequality, or relation, I should call each of these things, or inequalities, and that was this work right here. And we realized that z is z is bounded by 1 minus root x, which, the way this is drawn, it's kind of hard to see. The book has a drawing of this exact same solid, so you can refer to that as well, or something very similar to it. This is not actually convex here, where that red line is. It's actually concave, and it's just hard to draw that and really show that to the reader without putting a bend in it. If I had done it this way, it just doesn't quite give an idea what that surface looks like. So this is actually bent into the page and not out of the page as it might look, and that's what gives us that this xz projection cleanly. Okay, that's one of the hardest things to see in this drawing, but that's more or less how we put that together for use to determine this set E down here. It takes some practice, it takes a lot of thought, and it definitely exercises the work we did in the 3D coordinate system to start the course. So one more example. This is quite a bit easier than what we just did, and that is computing the volume of a rectangular region, or sorry, a 3-dimensional region E. And that's very similar to finding the area with a double integral. So the trick, once again, is no surprise, we set the function in the integrand equal to 1. If it's equal to 1, then whatever region E we're integrating over, we're just actually finding the volume, right? So with a 1 right here, really all we're obtaining is the volume. Just like if you integrated along to take it back to one dimension, in case we needed some motivation for the formula from section 12.3 that we previously saw, in one dimension, from A to B, the function 1 dx is, well, x from A to B, it's the interval length, B minus A. And length measurement is literally the measurement of one-dimensional spaces. How far apart are 2 points in a one-dimensional space? It's just the distance. It's the difference of the larger point minus the lesser point. Okay. For surfaces, that was for regions in the plane. That was quite similar. We had a double integral of the function 1 dA, and then for volumes now we'll have the triple integral of the function 1 dV. So that's our analog of all of those. So this, like I said, is an easier application, and part of that is because the function itself is just 1. So that eases up the work in our integrand. So compute the volume of E, where E is the solid tetrahedron bounded by the planes x equals 0, y equals 0, z equals 0. So in other words, the coordinate planes of the three-dimensional coordinate system, and the plane x plus y plus z equals 1. So we need to get a decent sketch of what that is. And we'll realize we can cut this many different ways. So this is the same region, the same solid that we looked at for a previous example. So, or after a little bit of work, we could, regraph all of these things. Points on this plane are when x is 0 and z is 0, y is 1. When y is 0 and z is 0, x is 1. That's to satisfy that equation. And similarly, z is 1 for x equals 0 and y equals 0. So we know the intersections of these coordinate planes with this new plane, just as we did before. And now instead of integrating it as a type 1 surface in this section, we'll integrate it as a type 2 or type 3, whatever one allows us to bound y by surfaces. Okay, and the only reason I'm doing it differently is just to demonstrate that method. Okay, so now what we're interested in is bounding y equals 0, which is the xz plane here. So the part of our solid that matters is this. It's just the y equals 0 portion of it. And it's bounded by this outward bit of the plane that travels to the right along the y-axis. Okay, so doing that in a natural order to express the solid E, we'd say that it's points x, y, z such that y is bounded by 0, and again, that is the xz plane when y is equal to 0, and it's less than or equal to 1 minus x minus y. That is us rewriting the equation of this plane by solving for y. Okay, so values of y range from 0 to 1 minus x minus z. That's moving from here to here, here to here, out of the page, at us, however we might imagine that. But y is trapped between those two surfaces when we move only parallel to the y-axis within that solid. So now we've got the surface bounds, and that turns out to be one of the harder parts of this problem. And we could consider one way, we need to consider the projection of these surface bounds onto the xz axis. We've handled y bounded by surfaces. Now we need to bound x or z by a curve. It looks like what we've chosen to do, because it's completely arbitrary, we could choose either one, whichever one seems more convenient. Looks like I've chosen to bound z by curves. So z is our next variable of integration, and it'll be bounded by the curve 0 to 1 minus x. Now what is that? Z is 0, that's along here, up to 1 minus x. So 1 minus x is that line, z equals 1 minus x is that line, and those are our bounds for z. Z is bounded by, it's a planar region bounded by these curves. z equals 0 and z equals 1 minus x. How did we get 1 minus x? Well, when we're in this plane, D is on this plane. Luckily, our solid intersects the xz plane. So our projection is just the intersection of the solid. And that turns out to be when y is 0, and when y is 0 in this, we solve for z to get 1 minus x. Okay, so those are the details of that situation. And lastly, the easy one to do, well, x is the free variable. It will just range from 0 to 1, and that will fully describe this solid. Okay, not only does it fully describe the solid, it gives our inner, second, and outer limits of integration. And we've done this with respect to y, then z, then x, as noted here. So our volume is of this solid E, function of 1 right here, over the solid E, becomes the iterated integral, y's range, z's range, x's range. And, well, integrating with respect to y, evaluating at these limits of integration, we have the upper limit minus 0, so we end up with this function. Integrate that function with respect to z, and we have, this is a constant with respect to z, so it's times z. Z integrates to 1/2 z squared. So here we have that. The sign, of course, comes along. Evaluate from 0 to 1 minus x. And below we have 1 minus x times 1 minus x is 1 minus x squared. Then negative 1/2, 1 minus x squared, or z squared. And those are like terms, like variables, 1 minus x being the variable squared. And so we have 1 minus 1/2, and we have a positive 1/2, 1 minus x, quantity squared. Integrate that with respect to x. There's some implicit chain u substitution taking place in the background. It just pops out a negative. 1/3 times 1/2 is 1/6 from the power rule. We're cubing that. Evaluate from 0 to 1. The result of this overall is 1/6. So that's a volume of one of these solids. Of course, maybe what I'd encourage the reader to do is to set this up in another way, to try to set this up as another iterated integral. Rewrite E and perhaps do it dx, dy, dz instead. So now bounded along the x-axis by surfaces, which would be this surface, and then it would be bounded by this surface on the back side of it all. Okay, it would be another nice practice for these types of problems, a good introduction to handling that. Either way, a lot of practice will be required because, as you can see, we've got to be able to read these solids cleanly back and forth from the limits of integration to the solid, or from the solid to the limits of integration.